I wanted to do a quick recap of the sort of discovery of the right triangle similarity theorem that we were working on in class, just in case you're a little bit confused. I know there's a little bit of struggle. So we're going to take a look at some student work and see sort of what the conclusion should have been. So basically we started with a picture like this, something like this. And I think we worked out that if the angle that we had here, if we're going to call that x, then 90 minus x would be the other angle. That would be, if I took and just put a number in there, if x is 50, then the other angle would be 40 degrees, 90 minus that 50. So what we end up with is we end up with those two angles the same. I'm looking at the two triangles next to each other, ACD and then BCD. And then they also end up with these two angles being congruent to each other. So when I reorient them, I have this real nice angle similarity. I know all three angles because they both have the right triangles, or the right angles. So notice that I did take triangle BCD and reorient it. This side ended up being this side, so that it's oriented the same way as my other triangle ACD, the one on the left. And then from there, we can also recognize that the big triangle, and just kind of like try to ignore this part in the middle and just look at the big triangle, has those same two angles. Of course, I'm going to keep that there. And then from there, I've got those three similar right triangles. And then taking and looking at the proportions, this is a lot of letters to look at, but what I end up seeing is that AD only appears in my small triangle right there. So if I'm relating that to my middle triangle, AD over CD is equal to DC over BD. So that's the ratio of two sides in those two triangles. That you were kind of prompted to do that. And then the conclusion there is that CD, notice CD is the thing that's in common there. CD is here and here. CD ends up being related because that is two different sides. It's the long leg in one triangle and the short leg in the other triangle. So that's how I get that proportional relationship. So CD ends up being the geometric mean between AD and DB. If you're looking at your picture, that means that CD, the altitude, is the geometric mean between AD, the left-hand part, and the right-hand part of that original hypotenuse. So that's an interesting relationship, but it all goes back to those two similar triangles. So not something that you need to really memorize, just kind of a conclusion statement that we can make. And then we follow suit for the other two. So the other two proportions that you were prompted to make, let's see. So we've got AB and so I'm finding AB is in the big triangle because that is the hypotenuse, the original hypotenuse. AB compares to, well, I got to compare that to one of the other two hypotenuses. And then DB is the other thing that I have. And I'm talking about DB here. That's the only place that I see DB. So it looks like I'm comparing the hypotenuses, AB to BC, and then BC or CB to DB. And those are comparing two parts in these two triangles, my medium triangle and my large triangle. If you want to label them small, medium, and large. So BC ends up being the connector here. BC is comparing BD to AB, or is the geometric mean between the one part of the hypotenuse and the entire hypotenuse is what ends up happening. So that's when I'm talking about BC. And then the last thing I've got, you're getting the idea here, is AC is essentially what I'm looking at here. So if you're looking at kind of common parts here, and AC, if I find that, is this side, the other leg compared to BC. And I have a hunch that that's going to be relating AD and AB, kind of the opposite of what we saw in blue. And if we take a look at that, AC, I know I got a lot going on here. AC is the hypotenuse here and the short leg here. So I'm going to be comparing hypotenuses, AB and AC, and then short legs AC and AD, and that's where this proportion is coming from. So now I'm comparing the small and the large triangles. So we've got small and medium triangles here. And we've got small and large triangles here. And this was the, oops, I think I did that wrong. I think this one was the medium and the large triangles. Sorry about that. And this was, original one was the small and the medium triangles. And that's another way to kind of look at it. So it's a lot just because I've got 3 of them going on, but hopefully that helps a little bit as we walk through that, and maybe gives you kind of an overview of what's happening here. Really nice summary statement. If a right triangle is divided into 2 or more right triangles, I think it's always going to be 2 by the altitude. So I don't know that we need this part. Then all 3 will be similar to each other. That's exactly what we should have been sort of getting at. And if you're interested in this, you can obviously like look up and memorize some relationships here, but it's all going to come back to the similar triangles. So I would encourage you to just redraw and work it out that way. I've got another video where I will go through couple examples before you try it on your own.